Okay, so last time we stopped at we actually talked about system calls, and we talked about the system calls and also the supervisor call. Um, oh, let me. People keep coming, so so we talked about the system call. So system call is basically a request from an application. When an application wants to, when you run any computer actual program, user program, when you try to, request for any hardware to use the printer or use the scanner or use request for any extra hardware resources. Now, the user cannot directly use the resources. So the user has to make a system call. Okay. So the system call is just like a function call. When you actually program your using when you do the program using Java or any uh, language, and you can actually write a method to make a call, and but in the system call is just like a method, but it's not implemented by yourself. It's actually created by the people who actually create the operating system. So the system call is the one that eventually going to actually trigger uh, one of um, the function called privileged instruction, and this privileged instruction is called supervisor call. The supervisor call is actually uh, is is actually created. It's called a kernel call. It's a privileged instruction. So you have to make a request. Okay. So then the operating system going to decide whether they're going to actually honor this or reject it. So so um, so one thing we need to remember is that when you actually run a program, when you run your actually user program, now the computer operating system has basically two modes. When you run your own application, then it's in the user mode. Okay. Now, when you actually make a system call to request a privileged instruction, then it will switch to kernel mode. Okay. So the CPU gonna have two mode, user mode and a kernel mode. When it's in the kernel mode, then even though the user requested for these instructions, once it's switched to the CPU switched to kernel mode, then the user has no control. You know, you have to follow whatever the instructions that are defined by the operating system. So because it's in the kernel mode, you have no control. You just follow whatever it is designed for. Okay, so that's the system call and the supervisor call. One of the important part of the computer operating system is the interrupt and the traps. Okay. Now, interrupt is very, very important in computer operating system. Okay. So modern computer systems are basically called interrupt-driven operating system. So modern operating systems are interrupt-driven. Now, what does that mean is that once you start your computer operating system, so when you actually turn on your power, and then the computer start to load the operating system from your hard drive, and initially load from your uh, ROM, which is then you start to load your operating system and into the computer memory. So once the operating system is completely loaded, now mostly the operating system going to be in some kind of idle state. So it's waiting for something to happen. Okay. So then when the user actually start the program, basically it trigger some kind of interrupt, So it's interrupt driven. Now, sorry, you have to apologize for. I have to apologize for this because I keep interrupted. So it's so I try to write something on the PowerPoint, but every time when I accept someone to join the Google Meet, then it just disabled this function. So okay. So basically, interrupt is an event that diverts current execution of the program to predefined location in the kernel. So what does that mean? That so for example, the operating system, the CPU is currently executing the instruction one by one. These are instruction. It could be a user program. Okay. Now when interrupt happens, then the CPU gonna stop whatever it is doing. Okay. It's gonna save the current state of this user program into the PCB, the process control block. Once it's actually still save that information into the PCB, and then the CPU gonna switch to to the interrupt. It's gonna actually start to handle the interrupt. Okay. Now the interrupt actually, once CPU complete the handling of the interrupt, then the CPU gonna actually come back and continue to execute this current user program. So the interrupt is something just once it's happened, CPU gonna stop whatever it's doing and to handle these interrupt event. Now, how this interrupt happens? Okay, so an interrupt is triggered by a hardware signal. It's sent to the CPU from external devices. Um, so so mostly, now here's what happens. So when a computer system, let me actually show this. Now the computer system basically consists of a couple of components. Here's a CPU, and then there's a memory, and then let me see. I think that's not a very nice drawing. So here's the CPU, and then here's the memory. Now CPU, memory, they are all connected to the system bus. System bus are shared by all the components in the computer system. And you can also see like a USB device, or it's connected through the USB, like a keyboard, mouse, or something like this. And then there's also some other device, I/O device, such as um, could be a disk. Okay. Now, the computer actually hard disk is actually connected to the bus via something called device controller. Okay. Or there's a monitor. Monitor is actually connected to the bus via also the controller, but mostly we call the graphics card. Okay. Okay, so typically what happens is every time when hardware requests to do something, so you're gonna actually typically send the interrupter to the CPU. Okay, so most of the modern computer system has another piece of component called the interrupter controller. Okay, the interrupter controller. So this is actually typically what happens. Okay. So now, if, for example, like a keyboard, okay, when a keyboard tried to actually, when someone actually press the keyboard, you know, just to press the key, like you want to type something. Now, the keyboard could basically, you know, send, the keyboard gonna send the characters you just typed into the controller as well. There's also a controller. And actually into the buffer in the controller. So when keyboard type A, character A, then that A gonna be actually sent to the buffer. B, this was sent to the buffer. And C, it was sent to the buffer. Okay, when you type each of the characters. Now when the buffer actually reaches a certain point, okay, so buffer is actually has a limited size. So it reaches a certain point. Now this, the buffer can actually trigger an interrupt. Okay, say, okay, I'm actually typing something, you know, so please actually process this. Okay, so the interrupter going to be sent from the controller of the keyboard to the interrupter controller. Okay, now the interrupter controller receive that information, then it will actually forward that information. So first we would know, because now in modern computer system, each device, hardware device, has a unique number. Okay, has a unique number. It's sometimes it's called device number, and many times it's called IRQ. Okay, it's called IRQ. So it's called interrupter request line. Okay, IRQ. So it is a number. It's a unique number. Okay. So for example, keyboard is, I forgot the number, probably 2. Okay. for keyboard, the IRQ is probably, IRQ number is probably 2. And then the disk has its own IRQ number. Okay. The monitor has its own IRQ number. So each hardware device has a unique number, device number called IRQ number. This IRQ number is basically used to uniquely identify the device itself. So when a keyboard sends an interrupt, it's going to actually attach the IRQ number. Okay, when the interrupt control receive this and check the IRQ number, now interrupt controller knows that, oh, this is actually interrupt coming from the IRQ number 2, which is keyboard. And then the interrupt controller going to actually inform the CPU and saying that, okay, I got interrupt from a device, which is IRQ, the IRQ number is 2. Okay, so the CPU actually received the interrupter, so the CPU going to stop whatever it is doing right now. And what the CPU going to do next is go to the memory. Okay. So the interrupt controller is going to inform the CPU about the interrupt. Interrupt happens. Who actually triggered the interrupt? In this case, it is the keyboard, which is IRQ2. Now CPU going to actually go to the memory location, one of the memory location in the lower memory location, and then CPU going to check one of the actually table. It's called, the table is called interrupt vector. So the interrupt vector is actually a table. That table lists all the IRQ number. Okay, so the IRQ 1, 2, 3. Now the IRQ2 is the keyboard. Okay, so that table lists all the IRQ number. Okay, so for each hardware device, that device has a number. So that number going to be listed in the interrupt vector. And then the table also points to the memory address. Each table, each actual IRQ number is corresponding to a memory address. Okay, these are different addresses. Now that's the address of the address of the something called interrupt handler. Okay. So now, so when you actually, when keyboard actually request, interrupt the CPU, then the CPU go to the interrupted vector and find the 2, and then find the corresponding address in the memory. So then the CPU start actually switch to that memory location. Okay, which basically stores the implement the computer program. That program is called interrupt handler, or something called interrupt service routine. Okay, so the CPU gonna actually basically load this address in its program counter. Okay, now the program counter basically tells this, eventually basically tells that okay, which contains the first instruction of the interrupter, handler. Okay, so that's interrupt handler, or something called you can also call interrupter service routine. Okay, so it's a program. That program is installed somewhere in the memory location, and that memory location is recorded here. The first instruction of this service routine is recorded here, okay, in the interrupter vector. Okay, so then here's what happens when the keyboard actually, when you type anything, once you type enough of the things, then the keyboard controller gonna actually send the interrupter. So the interrupter actually gonna to the interrupted controller. Interrupted controller actually inform the CPU. I think it's actually through. I put the line here, but it's actually through the bus. So to the CPU, and the CPU check the interrupt, message, and find out, oh, this is actually the IRQ2, the keyboard. So then the CPU go to the interrupter vector in the memory and check the interrupter vector and find out the interrupter IRQ number 2 and find the corresponding address. And then CPU basically load this address in the program counter, so start to execute the program. Now this actual program is basically designed to handle the keyboard activity. So typically, this interrupt service routine gonna go over there, check the buffer, and copy the character you just typed into the memory location, somewhere in the memory location. So you basically, when you type anything in a keyboard, eventually the character you keyed in will be actually copied into the memory. So, and once this copy complete, then so once you complete this actual service routine, then the CPU gonna go back to whatever it was working on previously. So as if that the interrupt never happened. Okay, so CPU gonna go back to whatever it was working on. Okay, so that's the interrupt. So the interrupt is basically, so CPU is working on something, and suddenly interrupt happens. Okay, then the CPU gonna go through this process I just talked about, and then finish the job and go back to the previous program. So that's basically the interrupter. Now, so if you actually go back, so you can see that the interrupter is actually it's basically triggered by hardware signal. So that's an interrupter signal. So it's sent to the CPU, and now more accurately, it's actually sent to the interrupter controller, and the interrupter controller forward the message to CPU and from the external device. And then the two most common use of interrupters. These are two most common interrupter use. One is signal to the OS the completion of I/O operation. Okay. So sometimes, when a program actually requests for I/O, there are two different type of, I/O operation. One is the blocking operation. So when a program is running, and suddenly request for I/O, and the program actually make a system call and request for I/O, and then the operating system is going to block this program. Okay, block this program. So then this program is not going to actually continue. So until the I/O job is done, then it will actually return back to the program and the program continue. This is one type of program. The other one is the interrupt. So when the program actually is running and request for I/O, and then once the I/O is actually requested, the program is not going to stop. Okay, the program is not going to stop, continue to do the work. Now, so then the I/O going to do its job. Once the I/O finish the job, then I/O going to send the interrupt to the CPU, say, okay, I'm just done with the job that the program requested me to do. So what's next? So then the CPU going to start to process and tell the program, say, yeah, I/O just finished the job. You know, what it's supposed to do. So these are two different schemes. You know, one is the program just wait, okay? The other way is the program actually request for I/O, and the program does not stop and continue to, you know, execute the next instruction. So in that case, you know, somehow the interrupter is actually used to tell the program that okay, the I/O job has been done. Okay, this is another way that they send the interrupter. Now also, the interrupter can be also implemented using in the time sharing. Okay, in the time sharing, interrupter is triggered by the clock. Remember the time sharing, right? If you have a multiple programs, multiple extra processes, so if the computer supports a couple of different processes running in parallel, okay, so then the CPU gonna switch back and forth between among these processes. Now, how does the CPU actually arrange these? It is actually through the interrupt, because in the time sharing, each process gonna actually take a certain amount of time, CPU time, okay? And then once the time actually, this period of time actually elapses, then the CPU gonna switch to another program and take the same amount of time, and then switch to another program. So when the CPU gonna switch back and forth among this program, how that switch happens? It's actually triggered by the interrupt. It's triggered by the clock. So if the clock is actually, the time is up, then it will trigger, you know, send the interrupt. It trigger the interrupt to the CPU, say, now it's time to stop, and you need to actually handle the next one. That's also via the interrupt. Okay. Now the another type of interrupter is called trap. Okay, trap is also actually, it's also interrupter. It can deal with the same way as the interrupter. So the trapper is, but the trapper is triggered by software. Okay, it's triggered by the currently executing instruction. So trapper is triggered by the software. Okay, trapper actually happens when the current program is running and suddenly some weird things happen. So, you know, like you know, you do the division by 0. You actually execute some kind of invalid memory location, then trap actually going to be triggered, and then eventually the trap are going to be basically send the trap ID, which is the same as the interrupter actually, you know, IRQ, the device ID. So the CPU going to handle the trap exactly the same way as handling the interrupt. Okay. So in general, an interrupt, whether it's external or internal, stops the execution of the current program. So save the state of the computation of the current program, and then transfer controls to the kernel. Okay. So the interrupt handler, or also called the interrupt service routine, is a kernel function. So it's invoked whenever interrupt occurs. remember how this interrupt handler invokes. It's actually invoked by the interrupter vector, right? The interrupter vector is the, like IRQ number, and then the memory address of the interrupter handler. Okay, interrupter handler. So this is actually interrupter vector. Okay, so the address of interrupter actually handler basically point to the interrupter service routine. It's just a program. It's a computer program, stored in somewhere in the memory. But it's in the kernel, because that interrupt handler or interrupt service routine is dedicated to serve the purpose of this particular hardware. Okay, so each computer hardware has its own interrupt service routine. Okay, each computer hardware has its own interrupt service routine. Okay, triggered by the interrupter. Okay. Now, how does this? Now the next question is, for each computer hardware, how can we actually install the interrupter service routine? Okay, it is actually part of the driver for the hardware. Okay, so every time when the hardware is installed in the computer system, so you also need to install the software part, right? It's a driver for this computer hardware. Now, when you install the driver, so then it will also update the interrupter vector and assign an IRQ number for this device, and add these particular line for this IRQ, and also install the interrupt service routine. Okay, every time when you add a computer hardware, you have to update the interrupter vector, assign the IRQ number to this device, update the interrupter vector, and install the service routine. Okay, so that way, so that's why the interrupter actually, every time when interrupter happens, it's pretty simple. The process is pretty simple, because every time interrupter happens, the CPU first check out who actually sent the interrupter. How does the CPU know who sent the interrupter? CPU just check the IRQ number. Okay, in the interrupter message, there's IRQ number. The IRQ number basically tells the CPU this is the actual device that sent the interrupter, and the CPU receive the interrupted IRQ number, the device number, and the CPU goes to the interrupter vector and find out what is the address of the service routine. So the CPU actually go to the interrupt vector, check the address, and then go to the service routine and then start to execute the interrupter service routine. So that's always the pattern. So for each computer hardware, when they actually interrupt the CPU, the same interrupt service routine will be executed. So it's a very simple process. Okay, do you have any questions? So then, every time when interrupt happens, you're going to eventually go through that process. So the CPU check the IRQ number, goes to the interrupter vector, and find the interrupter handler or interrupter service routine. Basically, I use these two terms interchangeably, and execute. Okay, execute the interrupter handler. Okay. So once the CPU completes the execution of the interrupt, now during the execution of the interrupter handler, CPU actually just process the hardware. For example, if it's a keyboard, typically CPU going to basically copy the characters that which is actually you keyed in from the keyboard controller, the buffer in the keyboard controller, and copy the character you keyed in from the keyboard controller buffer into the computer memory. That's what the service routine that the interrupter handler are going to do for the keyboard. Now for the printer, so the interrupter handler basically going to actually send the character into the printer controller, and then the printer controller going to send each of the character down to the printer, and so print each of the character. So for each hardware, the CPU going to always execute the same interrupter service routine or same interrupter handler. Okay. So when the kernel function terminated, when the interrupter actually handler, when the CPU complete the execution of the interrupter handler, now the state of the interrupted computation is restored and the control is returned to the instruction following the interrupter. So the CPU actually go back to whatever it was actually execute. Okay. That's the interrupter. Now this is actually the one of the example I'm actually we just actually work out. So yeah, that's just an example. Okay. So typically the driver basically when you run the program, when you execute the program, and suddenly the program actually make a system call to use the device. Okay, so disk drive. So then CPU going to make a system call, and so the step one. Okay, the step one here. The step one here basically tells the controller that what to do by writing into the device register. Okay. Okay. So the controller, so that's basically the first actual system call to start the disk drive, and by writing into the device register. And then the controller then start the device. Controller started the device. Okay. So the controller going to start the device. Okay. So when the controller basically finish the job, finish the reading or writing numbers of bytes, then the controller basically send the interrupter to the interrupter controller, and the interrupter controller basically forward the interrupter to the CPU. That's step 3. If the interrupter controller is ready to accept the interrupter that exists the pin in the CPU chip and tell the CPU there's an interrupter. So then the interrupter controller puts the number of the device. That's the IRQ number. Okay. So the CPU can know, okay, this is actually the device that the interrupted me, and then the CPU actually can read and know what device has just finished. Okay, so that's basically what happens. Okay. Now, once the CPU decide, okay, I'm going to take the interrupt. So then the interrupt process start. Okay. And then the CPU, the program counter, the CPU gonna put, check, basically check these. It's called dispatch to handler. So that's basically the interrupt vector. Okay. So basically tell based on the IRQ number. So then find out what to do. The IRQ number point to this actually service routine. It's a new instruction. Okay. Once it's finished the job, then it basically return. Okay. So this is basically how the interrupt happens. It's exactly the things I just mentioned in, previously. So that's basically the interrupter. So just keep that in mind that each hardware device has an interrupt ID. It's called IRQ. It's a unique for each device. Each device has a unique interrupt, IRQ number. It's called interrupt request line number. So that's a device. Some actually operating system book call it the device number. So that's the IRQ number. It's a device number. So every time when you install the device, then the operating system is going to assign a unique device number to that hardware. Okay. Now, once the device interrupt the CPU, you have to attach a device number. Tell the CPU who actually is interrupting. And the CPU then, based on the device number, look at the interrupt vector and find out, based on this IRQ number, the device number, then it points to the memory address of the interrupt service routine, the memory address of the interrupt service routine, and the CPU start to execute the instructions over there to start the actually service routine. That's how the interrupt happens. It's always like this pattern. Okay, so I think that's pretty much all I want to talk about for the interrupt. So interrupt actually, it sounds very complicated, but it's not really that complicated. It's pretty actually simple, process. So you can check the Xi book, and there's actually ammunition over here, so you can actually check how it works. You need to actually understand the interrupt from various different, direction. If the ammunition going to help you understand how these interrupts are going to be handled. Okay. Now the next 1.3, the evolution of and the scope of the operating system. So I'm actually not going to talk about this. I want you to actually read the Xi book, the section 1.3, because it's basically talking about the history of the operating system. So I think I'm gonna skip that part because we lost one class due to the snow. So but this part is basically just talk about the history of the operating system. So I'm not gonna actually talk about this. And so section 1.3, I'm gonna skip that part. I hope you can read it. And also after the 1.3, I actually add some additional slides and explaining the computer interrupt. So you can take a look at these additional slides. So these slides basically talk about how the interrupt actually happens. If you actually, the interrupt coming from the keyboard and how this happens, what's the steps, Okay. So please actually read this. I'm going to post this, the PowerPoint presentation on the Blackboard, so you can take a look to better understand what the interrupter is about. Okay. Do you have any questions before I move forward? Okay, let's start the next module. That's module 2. Okay. Now, so the module 2 is corresponding to chapter 2 in Zai book. So we're going to talk about the processes, threads, and the resources. So we mentioned the processes in the chapter in the first module, but we're going to talk about the processes in detail and how the process is working in the multi-programming environment. Okay. Now, what is a process? Okay. There are many actually definitions for a process, but they're basically the same. So a process is an instance of a program. Okay. So it's an instance of a program. So what is a program? Program is a computer code, right? Like when you write the computer program in Java, that's the code you just wrote. Okay, that's the program. Now, what is a process? Process is when computers start to execute the instructions for the code, and they start to actually, execute the program. Then that's a process. Okay, why it's called an instance of a program? Because a program is a statical one. So if the program is written, it's actually normally a program is stored in the computer hard disk. Okay. Now, once you try to run a program, so you need to load the program from your hard disk into computer memory. So you load the program into the computer memory. And a program is just a whole bunch of instruction. Okay. Okay. Now the program going to be executed by the CPU when the CPU is currently available, and then the CPU going to load the instruction, load each of the instruction into the CPU register. Okay. CPU register is a memory, a kind of a storage, a memory inside the computer CPU. And a special register called that the store the instruction is called the instruction register. We normally call it IR. Okay, it's called the instruction register. So once the CPU start to execute the program, it's executed the program, then CPU gonna actually load the instruction into the instruction register. Okay. And then the CPU gonna go through a cycle. It's called, so the first cycle is called fetch. So basically, you're gonna load the instruction into the instruction register. That's a fetch. And then the next step is called a decode. The CPU gonna decode. CPU gonna observe the instruction loaded into the instruction register and to see what should I do. So it just decode the instruction and then execute. Fetch, decode, execute. That's a cycle. a CPU cycle. Okay. So once your CPU complete the execution of this instruction, then the CPU gonna actually jump. CPU gonna jump to the next instruction and fetch the next instruction, decode, execute, and fetch the next instruction, decode, execute. So the CPU basically keep actually execute the instructions in the for that particular program, and this actually is called a process. Okay, so the process is actually so sometimes when you see the definition for the process, people are going to give a definition for the process as a process is a programming is a process is a program in execution. Okay. Now process is going to be, can be created when a user open a new application, like you actually start a new web browser. So when you start a new web browser, you basically double click the browser icon, which is actually a piece of program stored in your hard disk. When you double click it, you basically copy the browser program into the computer memory, and basically you start a new process. Okay. So each process is going to be stored in the computer memory. And then now modern computer can support multiple programs, so it's called multi-programming. So that means the computer can load different processes into the computer memory. So you can load the process 1, load the process 2. Process 1 could be a web browser. Process 2 could be a Microsoft actually Excel spreadsheet. Process 3 could be Microsoft Word. Process 4 could be, so you can actually load a different program, and once you load it, each of the program can be loaded into the memory as a process. And also, you can load the same program twice. So that means you can actually basically load 2 spreadsheet, Microsoft actually Excel spreadsheet. Okay, you can load 2, and then each of these is a process. So basically, you can actually create 2 processes from the same program. Now, each of these Excel spreadsheet basically is a different spreadsheet. It's what you're working on different spreadsheet, and these are 2 different processes. So there's a situation that you can actually load the same program multiple times. Okay. Now, if you actually open a web browser, so you open a web browser and you open another web browser, you open another actually the same web browser, you just open another twice. You open 3 times. You may open a couple of pages from the web browser. So you can actually, one web browser you actually look at the Yahoo. One web browser you look at the Google Gmail. One web browser you actually surf the website. So you open up different windows in your web browser. Each window is corresponding to a process. Okay, so you have multiple processes. Okay, and these processes may be actually associated with one program, the same program. That's a possibility. So, the operating system, once you actually start a process, okay, each operating system is going to keep track of each process using the process control block. So that means once a process is created, so when you actually launch a web browser, and you create the new process. And then once the new process is created, a data structure called the process control block is also created. Okay, so it's called a process control block, or PCB. A PCB is a data structure that holds the information for a process. Okay, so in the program, you may actually create one process, another process, another process. You create the three processes. Now each process is associated with a process control block, PCB. PCB 2, PCB 3. Okay. The PCB basically record the current status of the process. Okay. Now, each process, once the process is started, now a process actually has states. A process has states. Okay. Okay. So a process is always in one of the several possible states. Okay. So one is called the running state, and the another state is called the ready state, and the other state is called blocked state. Okay. So once the process is created, okay, so the PCB will be created. Now process is going to be in several different states. Okay. Initially, once the process is stated, is created, but the CPU hasn't started to execute the process, any instruction in the process. So these are the instructions for the process. The CPU haven't started to execute the process. So in that case, the process is in the ready state. So that means I'm ready. So hey, CPU, if you are ready, so you can pick me and execute it. Okay, so that's the ready state. Okay, now once the CPU actually is free at the time, and the CPU start pick up this process, and then CPU pick up the process by picking up the first instruction and copy fetch the first instruction into the CPU register, and then the process state switches to running state. Okay, so now the CPU actually start to execute the process, execute the instruction one after another. Okay, now during the execution, if the process is requested for I/O, then the process may block itself, right? So I'm actually waiting for the I/O to generate the output result for me. So I'm not going to be able to run at this moment. So it's going to be in the blocked state. Okay. Once that particular CPU finished the particular process completed the I/O, so it will be removed from the blocked state. Then in that case, this process is going to go back to the ready state. Okay. Or sometimes a process is in the running state after actually executed a couple of instructions, and then the CPU decided, the operating system decided that, okay, I'm going to switch to another process. So in this case, the operating system is going to save the current state of the information of the process and put the process into the ready state. Say, okay, I'm done. I'm going to actually switch to another process. So I have enough of you. So I'm going to switch to another process. So in that case, the CPU going to actually, the process, the state is going to switch to ready. Okay, it's not running state anymore because the CPU is actually executing another process. So these are actually you can actually, so during the lifetime of a process, basically the process is going to switch back and forth among these states. Okay, so this is sometimes called a state machine. Because the state is there's a finite number of states, so sometimes it's called a finite state machine. Okay. A transition from one state to another is performed by the operating system. So from here to here, from here to back to running back to ready, and from blocked to ready, and from running to blocked. So these are actually controlled by the operating system. Okay. So also, it's controlled by operating system, but it can be caused by process itself. For example, if the process actually change the state from running to block, it's caused by the process actually being executing an IO devices, right? So that's why the process just tell the operating system, say, hey, I'm actually I'm waiting for the IO result. So then the operating system gonna actually set the process to block the state, and then so the operating system can actually can run another process. Okay, so through the lifetime of this process, it's just basically switch back and forth among these different states. Now, these are three very basic states. Now, for most of the computer operating system, the process may have more states than these three. So these are three basic ones: ready, running, blocked. Okay, but in many of the computer operating system, there are some other states for the process. One of the states is called a new state, and also terminated state. And there's also called a suspended state. So that means there's when the process is created. When the process is created. So it is actually in the new state. Okay. So the new state means, okay, the operating system just created a new process. Now, before the process is allowed to compete for the CPU. Okay, so it's a new state. So once actually operating system say, okay, now you're ready to use the CPU. So in the ready state, and then ready state can convert to running state. Running state could be potentially go back to the blocked state, and blocked state go back to ready, and then go to the running blocked, and sometimes running actually is directly go back to ready, and then once actually running state, if eventually you keep running, and you complete the whole instructions, now it's in the terminated state. Okay, when the execution can no longer continue, but before the PCB is deleted, so it's a terminated state. Okay, and then no, terminated state means, okay, it's done my job. Okay, but the computer operating system hasn't completely deleted that process, so it's in a terminated state. Okay, sometimes a process may be placed into the suspended state, even though the CPU and all the resources are available. Okay, so that's called a suspended state. But it's up to the operating system. These three are basically a must, but these depend on the operating system. They may create this an additional state. Okay. Now the other important part of the operations in the operating system is the context switching. I think we mentioned the context switching, right? Because when you try to support multiple processes, each process has instructions. Now, the CPU basically pick this process and execute the process. And the CPU started the first instruction and run at this moment. And the CPU said, okay, enough. I'm going to stop you and then save all the information to the PCB. And then the CPU switch to another process. And another process start from the instruction that it was left in the previous time when the CPU left this process. It just finished that one, but then CPU gonna start from this one here. Okay, and then CPU gonna execute the instruction and stop over here, and the CPU gonna say, okay, I'm gonna save the current state into the PCB and switch to another process. So CPU basically switch back and forth. Now, when CPU actually switch from one process to the other, CPU need to save the current process, the information of the current process into the PCB, and then load the PCB of the new process into the CPU registers, and then start the new process. And this basically takes some time. Okay, so basically when CPU stop the current process, stop executing the current process, then CPU need to save the current process info into its PCB. Okay, and then load the process to be executed from its PCB and the CPU. So CPU stop the current process, but before CPU actually switch to the new process, CPU need to save the current information of the current process into its PCB, because you have to save it into the PCB, because when CPU actually later, when CPU come back to this process and continue to work, CPU need to reload the information from the PCB and resume the execution, because you cannot actually leave the process and without saving anything. And when CPU come back, CPU actually lost any information about this process. So these are the two things. Now, but saving the current process, load the next process requires some time, and this is called context switching time. So the context switching is the transfer of the control from one process to another. Now, each time when process stop executing to allow another one to resume, the operating system must save the information about the stopped process. So that's one. That's this. And then the information is restored when the process again get the chance to run. So the temporary interruption is fully transparent to the process. The information that need to be saved is called the CPU state. Okay, the CPU state consists of all the intermediate values held in any CPU registers. So because when CPU actually execute the current process, the CPU actually basically has many actually intermediate values loaded in the process and loaded into the register. And suddenly CPU say, okay, I'm going to actually switch to another process. Now CPU have to save all the information currently in the register into the process control block, and then switch to another process. Because later when CPU switch back to this one, CPU switch back to this process. So the CPU need to reload every data into the register and continue. So that's why a context switch is very important. Okay. I think that's pretty much all I want to talk about for today because we're running out of time. Now, so please actually go to the Zai book and start to read the chapter 2. In particular, check and first actually actually understand the interrupt in the previous chapter, chapter 1. And then for this chapter, I think the context switch is very important. And the process state context switch is the one you need to actually look at. Okay. Do you have any questions before I move forward?
Are we gonna do the homework inside book? When is it due?
It's actually today.
It's
But
due today.
yeah, I previously actually put as a February 4th, but I actually extended it today.
Oh, okay.
Please try to read the chapter 1 and do the exercises in there. So um, it's actually due today. Every time when I say due on February whatever the date, it means the end of the day. So that means the midnight. Any other questions?